In this video, I'll be demonstrating 3 ways to test a claim in statistics. Since this is our first assignment from the unit, I wanted to make sure that everyone was going in the right direction with it. So by now you've read the question and may have noticed that there was a small change that I had to make on the original question for it to be correct. And now that that's taken care of, let's just read over the information, and I'm going to begin by testing this claim by creating a confidence interval. So it says that the factory produces smartphones at a rate of 350 phones per minute. So that's what their target is. That's what they're claiming that their average amount of phones produced should be. And then after examining a random sample of 100 minutes, that would be our N, from the week yields a sample average of 348. So we're below where we should be, but only by a couple phones per minute. The question basically revolves around answering, should we be concerned about the fact that we are 2 phones per minute below where we should be? To help you make that decision statistically, there's one more piece of information that's needed, and that's the standard deviation. Anytime you're doing a statistical analysis involving averages, finding out where that standard deviation is coming from matters greatly. Well, in terms of being precise. So they're saying that this is a historical standard deviation from the company's records of 10. So that is not coming from the sample, that is coming from the population of all minutes recorded by the factory, that the standard deviation is 10. Now that we know that the standard deviation is coming from the population, we know that we're going to be using z-scores instead of t-scores. Okay, moving on from here, let's get on to the confidence interval. The first step is to check the conditions, and both of the conditions are met. Next is to inform the reader or the grader what type of interval you're using, and this one's involving z-scores, so this is a z-interval. It's nice to broadcast what formula you're using as well, and from here you can use the graphing calculator or place the numbers into the variables that they represent. After doing so, we're getting a margin of error that's approximately 2 minutes, and our confidence interval is between these two values. Now, to do a high quality job on this, we want to interpret what's going on by writing down a third step that explains what this interval is all about. And we can also answer the question, which is that 348 suspiciously too low? So my conclusion here is that the method used finds the true average 95% of the time. I'm using a 95% confidence interval since I decided to use a z-score of 1.960. Now you could have used any confidence level you wanted, but usually 90, 95, or 99 are the most popular ones. If you use 90% here, then you'd have used 1.645 here, for example, giving you a slightly shorter interval. But most important to us here is actually to answer the question, is that sample average of 348 suspiciously low? Well, since 350 is supposed to be the target time, or the target number of phones, 350 does not appear in that interval, and since that's true, that suggests that the true average is no longer 350 for the factory. In other words, the factory could be drifting off course in terms of their production. And the fact that the average could be as low as maybe 346 phones per minute, that's telling us that it's underperforming by 4 phones per minute. Now it's per minute, so 4 phones per minute, but you forecast that over an entire hour or an entire day or an entire week worth of production, and that'll be a significant difference between. So let's actually take a look at another way to solve the same question, and we'll do that with the central limit theorem. So if you're analyzing this with the central limit theorem, if we're told that the true average is supposed to be 350, we want to know how rare could it be that our sample drifts to 348 or even worse. So we'd have to figure out the probability underneath this normal curve from 348 off to the left, because we were trying to figure out how rare is it for a sample to be this rare or actually worse than it. And that's just done quickly by using normal CDF. Actually, this technique is probably the easiest way to actually analyze the question. I mean, there is the condition checks as well that must hold up, but you're just using normal CDF between negative 1,000 to 348. And then, there's a matter of getting our average, which would be the average that was stated at 350. And the only thing that's maybe holding us back is figuring out the standard deviation. It wouldn't be 10, because in this question, we're not dealing with the standard deviation from individuals, but we're dealing with the standard deviation of all the sample averages that are under this curve. Remember that this normal curve in the central limit theorem is filled with millions upon millions of sample averages. Most of the sample averages end up being very, very close to 350. Occasionally one might drift far to the right or far to the left, but most of them behave themselves pretty well, and their behavior, how close they are clinging to that 350, is based on this formula that the standard deviation of all those sample averages is the individual standard deviation divided by the square root of n. So for this example here, 10 is the standard deviation, and there were 100 in our sample. So our standard deviation ends up being just the number 1. So if you plug that into a graphing calculator, you end up getting an answer that's very, very close to 2%. And now it's just a matter of judging for yourself how rare do you think that actually is, and technically or statistically, usually a 5% or a 5% probability is considered to be rare, something that's 5% or lower, and this is at a 2% level. So it's not very likely to get a sample average that comes out to be that low. That should only happen 2% of the time. So the conclusion would be the same conclusion that was meant on the other technique. Which brings us to the last way to solve this, which would involve using a hypothesis test. So the hypothesis test has 4 steps. The first step is stating our hypothesis. The null hypothesis, or what we believe is true, is that the factory is producing, or what we're told is true, that the factory is producing 350 phones per minute. The alternative hypothesis is what we think is maybe going on behind the scenes, is that really maybe the true average is less than 350 phones per minute. These numbers should always agree in these hypothesis tests. You never discuss the sample in the first step, but you use the sample to make a decision sometimes on what inequality to use here. Since our sample average came out to be 348, that's below 350, so we're thinking that possibly that 350 is too high of a mark, that the true average is below. In the second step, you're going to be doing 3 different things to communicate what's going on. First is to name your test. This is a z-test, and that's because we're dealing with averages and the standard deviations coming from the population. We have to check our conditions. They're the same conditions that we checked before. It's a simple random sample, and the sample size is big enough. And then the last thing we need to do is set our significance level. So how low is a low probability? 5% is a nice choice, or 1% usually for these hypothesis tests. The third step will get you a little bit busy here. In the third step, you're going to be calculating the z-score officially on this. And the reason why we're doing that is so that we can replace that normal curve that I drew a few minutes ago with one that's much simpler where the average is 0 and the standard deviations are going up by the z-scores or going up and down by 1s. So getting back to calculating that z-score, we need the formula for it. So it's the statistic, take away the parameter, divided by the standard deviation of the sampling distribution. So once we place all those numbers in their right parking spaces, we end up getting a z-score of -2. So I'll find my z-score on my standard normal curve. I'm going to shade to the left because the inequality is a less than. And all that's left to do is figure out the p-value, which we already know from the last example, but when we're going to calculate it here, we'll also use normal CDF, but with a much simpler standard deviation because we've converted to a z-score. So that blue zone there would be -1,000 to -2, with 0 as the average and 1 as the standard deviation. Again, we end up getting a probability that's about 2%. And then we can make our conclusion that the p-value is low, so we're going to reject the HO, and we'll be in favor of the idea that the true average is below 350. So this is supporting the alternative hypothesis. All right, I hope this helped, and we'll be sticking with the hypothesis testing for a while. It's an important technique, and we'll be using different hypothesis tests depending on the situation.